Good afternoon, Professor.
Hello, guys. Nice to see you. Hope things are going well. It's getting colder outside. Soon will be quite cold here. Who is from Astana, like Nur Sultan? When we should expect some snow? I see, we should expect snow always. Okay, I think that some people are still joining.
Professor,
Yes?
are you currently in Astana?
Yes. I'm on campus.
I thought all the professors are also like students working at home.
No, some of them, but many professors are on campus. We just also work kind of at home. Most of the time, we're not allowed to go to the office, and there is quite strict requirement for going to labs. So those who have ongoing research, it's kind of important to be on campus because experimental science should be done here in the labs, but you need to pass this PCR test every 2 weeks and get some special permission from the university administration to go to the labs and also visit your offices. Since I just recently arrived, so still doing some paperwork and organize some basic everyday issues with moving to another country and another university. So I still don't have my lab up and running, so there's no need to go to the lab like the C4 building and S1, S2, I guess, where we have labs on campus. But in my case, just nothing yet done there. So over time, it will be changing, but we'll see how the situation going because it's kind of really a lot of restrictions to do research because of COVID. Also problems with equipment. Some equipment was already ordered, was delivered, even delivered on campus, but technicians from companies are not allowed to come and not allowed to install equipment. So it really messed up everything, but that's how it is. Need to deal something with this, somehow with this.
Oh, I see. It seems to me that it's problematic.
Yeah, it is. It is. It's just a hope that soon there will be a decent vaccine. But that's also not so easy and straightforward. So at least good that we have opportunity to continue educational process. Of course, it's not as good as it could be, but definitely better than nothing. Okay, do you have any questions regarding our recent topics of discussion? So just remind you that we, during this week, mostly a little bit at the end of the previous, discussed such concepts in physics as work done by force, introduced concepts of kinetic potential and internal energy, and described how this how work done by external forces is related to this kinetic potential and internal energies, how they can change and transform to each other. So introduce the concept of conservation of energy. And today, I believe we still have time. It would be good to continue with this topic related to conservation of energy and give you to consider a bunch of common cases which involve these concepts, and just to make it more clear how these concepts can be applied to different situations.
I have a question regarding week 5 assignment.
Yes, sure.
There is one mistake in the question, maybe. I have sent you an email. Can you please then check it and answer?
Yeah, so how we will do with this, if you find some mistake, because so far I heard about one mistake from other professors who deliver the course and like select these problems. There was an issue with the figure, I guess this force problem, which I send you a message. So there in the long kappa, it's wrong image. So you need to use that one which I attached in the email, or which is the link to this correct image is attached to the description of the problem. It should be there in long kappa. According to other mistakes in problems, so how we deal with this, once you submit your correct answer, and then make screenshot of your submitted answer, of long kappa's answer, and step-by-step solution of your problem, and send it all to my email. You can do it before the end of this assignment, or just to specify which. Also don't forget this screenshot of the problem itself, and claim that this is the problem. We will take this into account. We still are trying to figure out how to address issues which were highlighted by you and by ourselves later, which happened during the midterm. There was one problematic issue, and also during the homework assignment 4. So I believe it took a bit longer than expected, but I believe next week we will send you email and explain how we will address this. But if you see any problems now with current assignment or with future assignment, this is the procedure. Screenshot of the problem, screenshot of your solution, long kappa solution, and step-by-step solution of your solution of the problem. Please write your step-by-step solution clearly so we can read it. And then it will be taken into account. We will consider it, and if it's the case, we will proceed further with some corrections. Okay, do you have any additional questions? Good, then I think let's go and consider some cases which are based on the concepts of conservation of energy. Let me change the camera. Okay, so first let us consider a body on some surface, and there is certain friction, like some this body with the surface possess certain friction coefficient mu k. So let us assume that we apply external force to the body. It goes along axis x. Then we have obviously some weight, mg. Then we have reaction of the plane, n. And by applying this force, this body starts to move with constant velocity along axis x. So it moves to certain distance. And this distance will be delta x, let's say. So while it's moving, since it has this kinetic friction in the opposite direction to the constant velocity, we get kinetic friction force. So now the question is, what will be the velocity of this body while it moved from initial position to its final position at the distance delta x. So in order to address this, we need to consider what is going on here. We apply external force, and this body moves along the axis x in the same direction as constant force, this external force applied. So this means that this external force is doing some work. So there is work done by this external force is equal to the product of external force to delta x, since they are parallel to each other, the displacement and the force. Then we have some work done by kinetic friction. So kinetic friction, it is value of kinetic friction multiply delta x, kinetic friction force multiply delta x. And we know that we can write it like this. So it's mu a mg, because this is reaction of our plane, it compensates the weight, and delta x. So then we can apply this concept of conservation of energy. We don't change potential energy because this axis x is horizontal, so it doesn't change the height along movement. So we can write that kinetic energy at position 2, let's say this is position 2, this is position 1, is equal to kinetic energy at position 1 plus work done by external force. So this external force will increase kinetic energy, and minus work done by kinetic friction force, because that is where our energy, like this work done by external force, part of it will dissipate in transform in internal energy in the form of heat, will just dissipate, so it will be lost. Okay, let's see what we have. So kinetic energy at position 1 is 0 because initially it was not moving, so V is equal to 0. So this is 0. Then we have two works done. So it's external force minus mu k mg, and both like times delta x. Yeah, so kinetic energy at the position 2 will be defined as mv squared divided by 2, and this will be equal to f minus mu k mg delta x. So from here, we already see that we can express our velocity, which we are looking for. And it will be equal to square root 2 divided by m f minus mu k mg delta x. Okay, so this is the final expression for the velocity, and also just an advice for you, since you solve nowadays quite a lot of problems. The correct way how you solve problems, you derive first the final equation, which gives you the answer, the unknown parameter, and then substitute there all your given parameters. If you do this step by step and calculate some numerical intermediate numbers, that eventually can cause to some deviations from the correct number, which is in the long kappa. And since it's quite accurate in terms of like maybe about 1% deviation, that could cause some issues, and then you have kind of very close number, but still beyond this accepted range, and it considers to be not correct. So please try to do correct solving of problems and derive the final equation, then substitute all given parameters or all values. It will help you to get high accuracy eventually.
Excuse me, Professor. Can I ask a
Yes.
question?
Mm-hmm.
So why is in the figure where the body moves, why did you mark the bottom of the ground like you're neglecting the friction?
The bottom of the, you mean there were position of 2?
No. In the position of 1, like neglecting some friction of the ground, you marked the position 1.
Oh, you mean this like small lines on?
Yeah.
Oh, sorry. Yeah, I wouldn't say it's neglecting of friction. Sometimes, in order to highlight that there is a friction, you have some like tiny roughness on the surface, but it's not really some unified approach to specify by graphical representation if there is friction or not. It's given in the condition of the problem, for instance. So it's either tells you that you need to neglect this friction, or you need to take friction into account. So here it was specified that friction, kinetic friction, is taken into account, and I think it's not so relevant how you show the surface.
Thank you.
Mm-hmm. So you just start your solving the problem or considering any case based on given information in the text. That is the approach for these particular examples. Okay, so let us go further and consider similar case, but a bit more interesting. So again, let's have axis X, and this represents our surface. We have here our body, have mg weight, then we have force external applied at certain angle theta. So this is our force. Then we have some reaction of the surface, and also have some kinetic friction. So it also moves along the axis X, and from position 1 to position 2, and this displacement is delta X. Okay, in this case, we need to consider the fact that this external force is applied at certain angle. And the question which we would like to figure out will be the following: at which theta, angle theta, this body will reach maximum velocity.
Zero.
Let's see if we get 0, because there is some little trick hidden here. The thing is that this angle has not only limiting factor of force directed along axis X, it has some factor which also influence the kinetic friction force. If we have some component which is in the y coordinate, then we will reduce n reaction of the plate. And if we reduce n, then we automatically reduce kinetic friction. And then we need to find a balance, like some compromise between pulling force, which is along axis X, and reduced kinetic friction. So let us try to figure out what angle will be the most acceptable in order to reach maximum velocity. So again, we have to consider this conservation of energy, and kinetic energy in the point 2 is equal to kinetic energy at point 1 plus work done by external force minus work done by kinetic friction. Okay, so let us write down what all these letters mean. So mv squared divided by 2 for kinetic energy in the position 2. Then kinetic energy at position 1 is 0 because we don't have any movement, it's stationary. Then what is work done by external force? Then we need to take into account the projection of this force on axis X, and that will be F times cosinus theta times delta X. Then we need to subtract the work done by kinetic friction force. So here we need to be careful, because initially we would, like for the previous case, we would write m like mu k multiply mg. This is kinetic friction force, but it's not true in this case because now we need to subtract the projection of our external force on y-axis. And this will be F times sinus theta times delta, delta x will be later, like this, times delta x. So we subtract, we see that we have this component which is vertical. And this kind of reduces the weight. So if it's reduces the weight by this amount, we reduce the reaction of the plane. And in kinetic friction force, it is equal mu k times n, reaction of the surface. And if reaction of the surface is reduced by external force, we need to take this into account by this equation. Okay, now let us rearrange this a bit, and we can, let's write again in one line so it will be more convenient. Divide it by 2. Then here we can take out delta x from the parentheses. Delta x f cosinus theta minus mu k mg minus f sinus theta. Okay, now we can write for v squared equal to 2 delta x divided by m, and we have this f cosinus theta minus mu k mg minus f sinus theta. Okay, so I intentionally don't express v and leave it like v squared, because if we express v, we get this square root, and that will make our derivative kind of bulky. We don't want that, because the question is at which angle v, like the velocity, will be maximum. So if velocity maximum, then the velocity in second power will be also maximum. Oh, we have some question to show the previous slide. Yeah, you are welcome. If you need the previous slide. Yeah, is it okay? Okay, I guess. Again, if you miss something, I always upload this recorded video on Moodle, so you are welcome to check it there also. But if you have any questions, interrupt me and ask. That is very welcome. Okay, so if we have maximum velocity, then the second power maximum will be also maximum. So we don't need to express v and make our function more complicated. So now we don't have much space here, but still can maybe write. So what we need to do, we need to take derivative of v squared and over delta theta and set it to 0. So this is the condition of finding the independent variable at which function goes to extreme point. It's either maximum or minimum. So in our case, it's maximum. So dv squared divided by d theta, like maybe you can take in parentheses, will be equal, so 2 delta x m. Then we have derivative of cosinus theta will be minus sinus theta. So we will have minus f sinus theta. Then we go further. It will be constant if we open parentheses. So this product will be constant. It doesn't depend on theta. That's why derivative will be 0. And then minus and minus. So we have one minus before parentheses and one minus here and derivative of sinus theta will be cosine theta without any change in the sign. So minus and minus gives us plus, then we have plus here, f cosine theta. And yeah, I forgot mu k, which is in front of the parentheses. Okay, so this is our derivative. Let's go to try to remember it and go to another slide, so we will repeat it. So that's v prime, which is derivative of this function, is equal to 2 delta x divided by m. Then we have minus f sinus theta plus mu k f cosine theta. And this derivative we should set to 0 to find the theta at which velocity will be maximum. So means that obviously our, since delta x and mass, they cannot be 0, and like that, we need to take into account what is in the numerator. So delta x is not 0, it moved to some distance during some distance. Then the parentheses should be, everything what in parentheses should be equal to 0. Then we can write, according to this condition, that f sinus theta is equal to mu kf cosinus theta. So we cancel this out and we get that tangents of theta is equal to mu k. So this is the answer to our question. Tangents of angle theta, when it's equal to mu k, that will be the angle. If we take arctangents of mu k, we will get the value for angle theta, which gives us the angle at which velocity, final velocity of this body will be maximum.
But it also could be minimum.
Huh?
But it also could be minimum.
Yeah, but minimum that automatically is solved, because minimum velocity will be when you get either force equal to 0, or, I mean, sure, there is another option when you pull up the body. So it will give you two solutions, but you just you check what is physically reasonable and then get this numerical value, because mathematics doesn't care if it's physically reasonable or not. So you always need to look at your solutions, like your final equations, in the plane of physics, and consider the physical reasonable solution. You see that the force is directed, like you have some positive projection of force along axis x, so you cannot get the minimum velocity, which will be 0. So definitely the physically reasonable solution from these two will be the correct answer to this problem or case. But you are right, mathematically, it gives you always all options, so it gives you all answers to your equation. And in particular, when you apply this concept of taking derivative to figure out what will be the minimum or maximum. So when, at which value of independent variable your function will reach minimum or maximum, that will be your answer, but you need to figure out which from these solutions of equation is physically reasonable. Another thing that you can also take second derivative is like another mathematical approach, and check what value, what is the sign of second derivative within this point of extreme. If it's like positive and then switches to negative, or negative switches to positive, but that is already more calculus than physics. Okay, guys. Let's go to another example. Let's consider a system of two bodies which are connected with not stretchable and weightless thread, like some rope, whatever, call it as you want. But in addition, we have some spring here. So the system will look like this. We have some spring with spring constant K. Then we attach some M1. Then this mass is attached. So this is on some surface with some friction. So let us mark it, some roughness here. So we remember that here we have friction. Then this is end of our surface. We have some block here. Rope goes like this. And we have M2. Okay, so this mass 2 is fixed, and at some point it just released. So under this weight, this mass 2 will move to y distance h. Since this rope is not stretchable, obviously that this guy will move the same distance, but in the different along different axes. So this will be M2, and this is also distance H. And this spring will be extended, so it will extend up to here. Okay, so let's say we know both masses. We know spring constant, and we know the this h, the distance this body moves. So the question is how we define mu k, the kinetic friction coefficient between body M1 and the surface. So again, we need to take into account the law of conservation of energy, and we can write that change in potential energy plus change in kinetic. I mean, here we don't consider kinetic energy. So we have two potential energies. So change in potential energy of gravity, then change in potential energy of the spring. So because, I mean, we don't have any velocity at the beginning and at the end. So we kind of don't consider change in kinetic energy. In both cases, we have stationary conditions.
Excuse me.
Yes?
M2 was pulled or released into its second position?
No, it was released. Yeah.
Okay.
No, we didn't apply any force, so it was released by its weight. Then we have change in internal energy because we have some friction, so we will dissipate some energy. And in total, this will be equal to 0 because for body M2, we reduce its potential, gravitational potential energy. And for body M1, we increase its potential energy because we stretch the spring. This, of course, it will be less change in increase in potential energy of body M1 in comparison to decrease of potential energy for body M2 because we have some kinetic friction, so we transform part of this potential energy change of body M2 in some heat, and that will be dissipated. So let us write equations for this. First, we will have minus M2 GH. This is change, reduction of potential energy for body M2. Plus, we have potential increase in potential energy of the spring, this body M1. So it will be K H squared divided by 2. So we know that potential energy of the spring is determined as a second power of its extension or compression. And then we have plus this energy, which like work done by kinetic friction force, which is mu k mg multiply delta x. So mg is like reaction of this plane, and so we don't have any forces in y direction, so that's why n is equal to mg, and this can be set to 0. So here what we can do, oh sorry, delta x is not delta x, we already have another letter for the displacement, which is h. Okay, so now we have everything correct. So we can cancel out this arch and square.
Sorry, Professor, why is the potential energy is with minus, like minus M2 GK?
Yeah,
H.
good question. So we see that it is initial position is higher and lower position, like this final position is lower. So if we have here axis y, then let's calculate change in potential energy. It will be M2 J. Let's have this coordinate y2, and this one, sorry, this is initial. This will be y1 coordinate, and this one will be y2. Then we have change. We need to subtract potential energy in second position from potential energy in the first position. So M2G y2 minus M2G y1. Then we see from this axis that y1 is larger than y2 because axis y is directed upwards. So if we can write here M2J, and here is y2 minus y1. So y1 is larger than y2. That's why delta y, which is actually h, is negative. And we get minus M2J h. So this minus means that we reduce potential energy of body 2, which is M2. And since we reduce it, we have this minus. And this is, if we recall what we were talking about last time, there was a relationship between work of conservative forces, internal conservative forces, relationship of this work to change of potential energy. And we mentioned that any work done by internal conservative force, which is gravity in this case, causes reduction of the potential energy of the system. And in this case, we release body M2, then gravity does some work. It moves body from position 1 to position 2, and that is causing reduction in the potential energy. That's why we have minus. And for the spring, we extend it, so we accumulate potential energy. So this is positive. And also we have some energy which is dissipated in some increase in internal energy. We heat it up because of friction, and that is also in this case positive. So we consider kind of absolute values of changes in potential energies and internal energy. So from here, we can already express mu k. Mu k is equal. So what, let's move these first two terms to the right. It will be M2G minus KH divided by 2. And all this, oh, sorry, here should be M1. And here we have M1 divided by G. So maybe it would be better to rearrange it a bit. Mu k is equal to this. So this is our answer to this question. This is the way how we would calculate the kinetic friction coefficient, if we know M1, M2, and K, spring constant, and measure the H, the displacement of two bodies. And all this possible to be solved by applying this concept of conservation of energy. Okay, guys, I think that it's pretty much everything for today. We're already running out of time. So these are some examples how these concepts of kinetic and potential and internal energy can be applied to some interesting cases in physics. And I believe you will have many problems to solve on this topic. So hopefully it will help you. We will meet on Monday next time. So yeah, if you have any questions regarding this, you are welcome to ask me. And also, I think that already on Monday, we will start working on the momentum. So we will consider new concept in physics, which is also very important and will help us to solve different problems. Okay, have a good weekend and take care.
You too. Goodbye.
Thank you. Bye.
Goodbye.
Bye.
Thank you.
You're welcome. Bye. Bye-bye.